Hi guys, so in the previous video we talked about ionization energy, what it is, and we also discussed two of the trends in ionization energies, which is successive ionization energies and ionization energies down the group. Now in this video we're going to be focusing on ionization energies across the period. Now generally ionization energies increase. However, there's an emphasis on the word generally because there are going to be some exceptions and we're going to talk about those later. So this is period 3. This is the list of elements that are there in period 3 with their proton numbers listed down over here. As you can see, the proton numbers are constantly increasing. Now I've written down the O-level simple electronic configuration for each of them. So sodium is 281, magnesium is 282, aluminum is 283, and silicon is 284, and so on. It's just going to keep on increasing that way. So now as you can see, the proton number is increasing, right? But electrons are entering the same shell. So the number of shells over here is 3. Over here is also, it's the same thing. You have 3 shells for each element. So the electrons are entering the same shell, right? So that means they're going to experience the same amount of shielding from the previous shells. Because before that, you're going to have 2 shells only. So every single electron over here is going to experience the same amount of shielding, right? So because of that, shielding will not affect your ionization energies. I think we discussed in the previous video when we were discussing electrons moving down the group. Since the number of shells were increasing, the amount of shielding was also increasing. However, in this case, the number of shells are the same. So the shielding is also going to be the same. So shielding will have no effect on the ionization energies. However, as you can see, since the proton number is increasing, right, your nuclear charge is increasing because your protons are found in the nucleus, right? So the overall charge of your nucleus is going to be increasing. So because of that, there's going to be greater nuclear attraction. Now over here, as you can see, you have your nucleus and it's surrounded by orbits, and these have electrons in them. So if your nucleus has a greater charge, then it's going to attract more electrons towards itself. And because of that, your atomic radius is going to decrease because all the electrons are going to be pulled in closer by the nucleus, right? So since the electrons are pulled in closely and they're pulled in very tightly by the nucleus, a lot of energy is going to be required, and this is why the ionization energy generally across the period increases. So like I talked about previously, there are going to be some exceptions to this rule. Now this is the graph for period 3 and this is the graph for period 2. Now as you can see, it's increasing. There's a general increase and there's a general increase over here as well. But you can see there seem to be some sort of exceptions as well, and I'm going to highlight those exceptions right now. So there's an exception over here. There's an exception over here. In this case, you have one exception over here, and then you're going to have one exception over here as well, right? So in this case, let's take a look at period 3. The first exception is going to be magnesium and aluminum. So if you write down the electronic configuration for magnesium, the proton number is 12. This is what you get. You get 1s2, 2s2, 2p6, and 3s2. For aluminum, it's going to be 1s2, 2s2, 2p6, 3s2, and 2p1. As you can see, this is the this is the valence electron over here, and this is the valence orbital over here. Now in this case, there are 1, 2, 3 orbitals before, right? 1, 2, 3 subshells before, and over here you have 4 subshells before. So as you can see, the outermost electron in aluminum is in the 3p orbital, whereas in magnesium it's going to be in the 3s orbital. So that's why it's going to experience less shielding, right? So since magnesium experiences less shielding, it's going to have a greater ionization energy than aluminum. Now you would expect aluminum to have a greater energy. Why? Because it's going across the period. However, this is going to be one exception to this rule. Similarly, if you take a look at period 2, beryllium and boron. Now this was supposed to be a little bit down over here. So if you take a look at beryllium and boron, the electronic configuration for beryllium is 1s2 and 2s2, and for boron it's 1s2, 2s2, and 2p1. Now as you can see over here, In boron, the valence electron is in the 2p orbital, and in beryllium, it's going to be in 2s. So this is going to experience more shielding. So boron is going to have a lesser ionization energy than beryllium. So these were the two exceptions that we discussed. This is basically the first exception, and we talked about the two examples. So the first exception is in terms of shielding, and there's another exception which is in terms of electron pair repulsion, and we're going to talk about that on the next slide. So if you remember in the previous slide, I highlighted that there's an exception between phosphorus and sulfur in period 3. Now if you write down the electronic configuration for phosphorus, this is what you're going to get. And for sulfur, this is what you're going to get. So over here, the number of shells that you have are going to stay the same, right? So shielding is not going to affect anything. However, if you take a look at 3p3, this is what you're going to get. If you take a look at 3p4, this is what you're going to get. Now as you can see, over here all the electrons are arranged singly, whereas in this case there's going to be a pair of electrons over here, right? And the other exception is in period 2, which is nitrogen and oxygen. Now in this case also the number of shells are going to be the same, right? So the amount of shielding is the same. However, if you take a look at these orbitals over here, so you have 2p3, right? So this is going to be arranged singly, whereas in 2p4 there's a pair. So whenever there's a pair of electrons, they're going to experience electron pair repulsion, right? So electron pair repulsion is actually going to lower the ionization energy. So because of that, the first ionization energy of oxygen is going to be less, and the first ionization energy of sulfur is also going to be less because of electron pair repulsion.